Yeah. Thanks, Ashish. Thanks everyone for coming. It's my first visit here at CS at the CS and Math and at Rutgers. So very nice trip. So I'm Wuyang. I'm from the Computer Science Department from Stanford First University. It's in Vancouver. So now many machine learning conferences are actually happening in Vancouver. So if you have time to attend any conference, feel free to drop by. So my topic will be about how to build hybrid learning machines that can bridge AI and physics modeling. Actually, before my talk, I think you'll find that actually I also find myself in the middle of the computer science programming language and the math, some kind of in the middle ground. So you'll see largely that my topic will be connecting different pieces in CS, in AI, and math and physics modeling. So that's also how I see my job is. Right. So we know that before AGI, or I'm not sure if we are heading to AGI or not, but actually before all these large models come out, we know that the humans generation is actually very slow. Human needs to take years to write these notebooks or scientific literatures or these paintings. But in contrast, human actually needs like minutes or hours or at most days or weeks to consume and read and reason around all these creations. Oh yeah, sure, yeah. Decades. Yeah, yeah, of course. Yeah, decade to appreciate. But if you really want to quickly go through it, it's relatively faster. But now you know that things completely changed. So for these generations, it at most takes a few minutes or like 10 minutes. So that means now everything totally changed. The generation is much faster. But in contrast, humans reasoning and human reading, human reading or humans consumption of all these generations are much more slower. So actually, it happens to me a lot. I'm not sure if, to you, but whenever I turn on the survey mode, the ChatGPT generates a whole bunch of articles, and I may not even have time to read them, and then it just quietly sit in the folders. If we turn on this agent mode, they can do a lot of plannings for us. This also happens to the video generation for all these kind of videos. Although these videos are actually not very long, but it also takes much shorter time than humans recording and movie filming. So that means we are concerning about how to align these generations with human reasoning, because if we just let alone these models to feel free to generate all these crazies, then human definitely don't have the resources or time or efforts to verify the correctness and fidelities of all these generations. So we definitely want to find some ways to roughly verify all these generations are aligned with human intents, human standard. So I'm going to talk about this just in a few minutes. But nice catch. Yeah. So it seems to me, at least to me, that maybe this question are a little bit infeasible. But I will gonna show that there are a few parts that we can actually work with. So it's not totally infeasible or unrealistic. So for the text part, for the text generation, we find that in many cases, we find these equations or codes, which are actually highly structured text. That means we may find some ways to verify either symbolically or its semantics. So that means for this text generation, if we only focus on the equations or the codes, we do have ways to either compile them or verify them. And same thing happens for the video generation. So if you look at the background of this video, clearly it's an ocean. Essentially, it's fluids. So we have some governing equations to simulate its dynamics. And as I promised that, so these two videos are actually, one is from the real video, that this on the right hand side is the generated ones. So you can see that even for this free fall, very basic rigid dynamics, if we send these same first frame to the video generator, you will see that even for this free fall, this video generation cannot reproduce very well. So that means not only for this more challenging fluid dynamics, but for this free fall dynamics, we do need to find some ways to verify the objects. So all these examples except this one, yeah. Right. So that means we actually have different cases. We have different standards for these generations. So that means, so these examples actually give us some hints or intuitions that actually for our pieces, novels and paintings, we actually have a very high tolerance on this generation. Actually, we may even welcome these creative, imaginative generations. But it is for those critical parts that especially related to either engineering problems or scientific problems, we absolutely have no tolerance on any conflicts with humans' intents or humans' common sense. So that means we really need to divide these two cases when we want to verify these generations. Right, so that means to answer the question that how to align generations with human reasoning, we progressively dive into more details that the generation should align with human common sense. And then moving one step forward, we ask, where do our human common sense come from, right? So we know that our human common sense is actually rooted in our physical world because that's how we human perceive and try to explain and summarize all these principles that's happening behind our physical world. So that means our human common sense is rooted in our physical world. Then we connect these two dots. That means if we want to align generation with human reasoning, that means we should align this generative AI with physical modeling. So that's how we connect these rationales step by step. We know that in general, when scientists try to model our physical world, we have different kinds of scientific tools, and I categorize them into two types. The first type is to include the symbolic modeling. Basically, we use different kinds of logic solvers, and we either write code or write equations or summarize them into theorems. On the other hand side, we also have these numerical modelings. Basically, they are numerical simulations. One typical example is the computational fluid dynamics. On the other hand side, we have the AI. We know that it's largely data-centric. So one naive way to connect them together is that we still switch to the pure data-driven, where we collect a lot of data and embed this modeling and these rules as regularization when we train these models. But in this talk, I will try to advocate another strategy, which is we want to build some hybrid models where we actively integrate AI and scientific tools. So that means essentially you will see in many of my examples that the ultimate solution is not directly predicted or generated by this data-driven models, but these data-driven models need to actively leverage and manipulate these tools, and these solvers will essentially give the solution. Yeah, question. Yeah. Mm. Mm. May not directly including the reinforcement learning, but mostly to solve the math problems or physics problems or to simulate some dynamics. Mm, mm, mm. Yeah. Mm. Yeah. Yeah. Right. Yeah. Thanks for the question. So I think it really case by case. So, for example, for the language models, people do need to split the training or post training into stages. So usually the supervised training, or basically you have ground truth labels. This training will be much more stable than reinforcement learning. For reinforcement learning, you really need to carefully design the reward. So the reward shouldn't be too hard or too easy. Yeah. And there will be different cases for the vision part. Yeah. Yeah. Sure. I think that so I think the data will be more related to the numerical modeling, but for symbolic modeling, I think for the modeling itself, we are not that much concerned. Mhm. Yeah. Uh, yeah, those PDs will be more related to the numerical modeling part. Yeah, yeah. Thank you. Sure. Mm-hmm. Mm-hmm. Yeah, for sure. Yeah. Mhm. Yeah. Traditionally, people definitely need to all these hairs, snows, waters. They need to really simulate this. I mean, from a graphics perspective, they definitely have some different ways to simplify the simulation, but largely they need to run simulation. But you may heard that nowadays people do consider if this generation model can make all these dynamics cheaper. Yeah. Mhm. Yeah, for sure. Yeah. Mhm. 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 That's true. Yeah. Yes. Exactly. Exactly. So, actually, I just finished my course. My teaching this spring is about the fluid animation for computer graphics. So, fluid solvers for graphics and fluid solver for CFD purposes are totally different. Yeah. Sorry. Yeah. Sure. Mm. Yeah. Mm. 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 Yeah. Yeah. Mm. 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 I see. I see. Yeah. So I think the parts I will involve will be more related to the first part. That's we use solvers to generate the data, and we do have ways to try to refine the quality. Yeah. Mm. Mhm. That's a good question. So I would say that my group try to serve both purposes. Uh, I mean that's a little bit away from the talk, but I can just add two more sentences here. So traditionally I'm an AI person. definitely I need to serve for lots of AI applications purposes. But I had my postdoc in a scientific machine learning group where they have lots of scientific data. So for those data, definitely they have much more rigorous standards. They serve for the scientists. So to maintain all these collaborations, I need to serve for both purposes. All right, so let me continue. Um, right, so this rationale will lead to all the recent projects in my group. And beyond the purpose of building hybrid models, you will see that we have two other rationales. One is that we will actively integrate these solvers with data-driven models. So as I mentioned, that you will see many solutions are actually coming from the solver, not from the data-driven models. And also to echo your question, so in many of our cases, to actually train our data-driven model, we still need to collect data, but you'll see that our data or many feedback or preferences embedded in our data are actually filtered by our scientific tools. So actually, my group work on two parts. One is for the scientific symbolic modeling, which will conduct the language model reasoning with the scientific symbolic modeling. I will mainly talk about PD control problem and the PD analysis problem. And we also do complete vision, as I just mentioned. The complete vision part will be more related to the 4D generation and reconstruction with the numeric modeling, which mostly involve either the fluid dynamics or the fluid reconstruction. I think this seminar is more about the AI format, so I will mostly focus on this part, but I will very briefly go through a few slides for the numeric modeling and the computer vision part. All right. So yeah, I will mostly focus on the first part. And so the goal of the symbolic modeling is in my project, will be involving the PD control, which will use the formal methods to control PDs. So the rationale is that if we can create if we want to better understand the PDs and its dynamics, it's better to create some solutions and the external control variables. And we are also involved the PD analysis, where we do the formal theorem proving for PDs. So the rationale is that if we want to create better, that it will be better for us to further understand the analysis or properties of PD solutions. And what is symbolic modeling? I think this is very familiar to most of the audience here. So basically, we want to do the reasonings using code or some domain-specific languages and some logic solvers. And some famous example are recently like the AI for math, such as the alpha geometry from DeepMind, and also theorem provings with Lin and some language model provers. So why why symbolic modeling definitely is verifiable. And another benefit that I see is that in this symbolic modeling, we humans still have chance to read and write and intervene this whole process. So it's not a total black box when we do this modeling and reasoning. And two bottlenecks you will see actually are two motivations to my project is that first, we want to replace human efforts in this process. So we want to know if the language model can actually replace human efforts in, say, the auto-formalization and proof generation or the code synthesis. And a more interesting problem or interesting part to me is that sometimes we don't want just naively replace human efforts with language models. We want to see if language model can outperform human efforts. I think that will be the more meaningful gain when we switch to language model. So that means the second bottleneck is that can language model outperform human efforts? So these are two bottlenecks that drive my projects. All right, the first project is about a PD control. So it's a paper about a PD controller where we do use the language models for auto-formalization and reasonings for PDs. So in general, the PD models physics systems. So that means if we can control PDs, that means we can have ways to control the systems. So here are two examples. If we want to control the temperature distribution in this room. So that means we need to control the power to this AC. So if we simplify this scenario, so suppose we have the 1D material, we want to control the spatial temporal dynamics of the temperature, then we want to apply this heat source. So the power we change to this heat source, then the dynamics will also change. And similarly, if we have the wave problem, then if we change the magnitude of the force applied to one end of this material, then we can also change the deviations or replacements of this displacement of this material, also temporally and spatially. So essentially, the final outcome of this task, we have two visualizations. So the first visualization is about the spatial temporal dynamics of this system. So here I use the wave equation as the example. The y-axis shows the displacement along this material. And this material has 100 meters as the 1D domain. And we show the temporal domain as the animation. So here, the colorful bars indicate the linear constraints. Essentially, we want the solution of this system to satisfy these spatial temporal constraints in certain spatial temporal range. And to satisfy these constraints, we need to control the magnitude of this external variable. So here, one solution we can find is to change the magnitude of this force according to these dynamics. So if we simulate the wave equation according to this external variable, then we can ensure that the system behavior will evolve like this. So the ultimate goal is that given a problem defined by human, basically the equation we want to use to model and the spatial temporal constraints, we want to find a solution that can satisfy these constraints. So that's the purpose of this problem. So traditionally, how humans solve this problem, right? So first, engineers or scientists need to define this problem. What kind of PDs and what are specifications? Definitely, we also have some initial conditions. And then here comes the manual efforts. We first need to formalize these constraints and PDs into a constraint optimization problem. And then we can use some existing optimization solvers to solve this optimization problem. So basically, we embed the variables and constraints into this solver. So here comes to the two bottleneck I just mentioned. That's first, we want to see if the language model can replace human efforts. So basically, if auto formalization by language models can automatically formalize these constraint problems. And then if the language model can synthesize code that can automatically run the external solver to solve this problem. And beyond, as I mentioned before, that we are also curious about the reasoning part, which means can language model outperform the human control and achieve some better control utility? So these are two ultimate questions we want to answer. So here is our overall pipeline. I just leave an impression here, but I will slightly dive into more details later. So originally we have the data, which essentially define the problem. Our prompt includes both the instructions and the problem definitions. And we have a language model that will do the translation work. So basically, it will translate the nature language, informal language, into some formal languages. And where you will see that the constraints are much more better organized. And we further have some metrics to quantify this formalization. And then based on this formalization of the constraints, the coder language model will synthesize the Python program. So inside the Python program, it needs to embed both the initial conditions and constraints. And if this Python program is bug-free, then it will call the Groby optimization solver to solve this PD control problem. So in this current pipeline, we will solve from the initial condition to the end of control, where we can calculate the ultimate control utility to quantify the quality of these control purposes. So if you find the utility is positive, the more positive, the better. But if the utility you find is negative, then that means this problem is not solvable. Yeah, sure. Mm. Okay. Mm-hmm. Yeah, I don't think we have to use Python. Part of the reason is that the solver, essentially the optimization script is originally written in Python API of the Groovy. Yeah, so and largely the purpose of this work is not to redesign the solver, but to bring the pipeline. Yeah, sure.
Much more naive question. If you're solving the heat
Yeah.
equation, solve heat equation,
Yeah.
why not just take his
Yeah, it is possible. But I think one issue is that so the purpose is not to just to simulate the equation, but to find the dynamics of the external variable that can satisfy the solution to the constraints. So essentially, it's a little bit different from the numerical simulation where you iteratively solve the linear systems, but you need to find the solution that can satisfy the linear system to the constraints. So I think it will be, and you need some numerical solution. So I think it's something beyond just apply the fundamental solution to the heat equation. Yeah, 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 yeah. Mm. Oh, okay. So I didn't include any functions in our generation that cause a groupie, but I can roughly say that essentially this whole problem will be formulated into a mixture of integer linear programming problem. And this groupie solver will use the branching heuristics to find the solution. Mm. Essentially, we want to, and let me go back to this part. So if I need to call a solution, so this will be the solution. Because essentially we want to find the dynamics of the control variable that can satisfy these constraints. But if you only run the simulation, so traditionally in PDE domain, this will be the solution. But here is uh, I wouldn't call the PD solution is parameterized. So we will have some variables or initial conditions that parameterize the problem itself. And if you only run the PD solver, then it will give you the dynamics. But we want to, because we have another variable here, say the force or the heat source. So this actually will be the key variable that we want to solve to control. Actually, I have more concrete examples, so you may find, yeah, sure, yeah. All right. By the way, do we need to sharply stop at 3 or? Oh, okay. Then I have another half an hour. All right. Right. And here you will start seeing that in the whole system, my language models will actively interact with the scientific tool. So essentially, this solution is calculated by the solver, not by the language models. Okay, here is the concrete example. So in our prompt, we do have the instruction and the target problem. So instruction is quite naive that here is the natural language description of the PDEs and please translate them into LaTeX code. So in this problem itself, we have the constraints, say, essentially it's a linear inequality for a certain spatial temporal region. We may have multiple constraints. We have some blue parts, essentially the geometry and the initial conditions. So we have all these details. So these numbers are parameters or hyperparameters that define this problem. So we definitely don't tune this part. So this is a case by case. And then this translator language model will try to understand and extract these constraints and formalize them into LaTeX code. So we all see that in this LaTeX code, it will much more well organized, where these constraints are written into the domains and inequalities and with some junctions with that connects multiple constraints. So that means this constraint is much more well organized than the informal natural language. And then this coder language model will take the constraints formalized and then write the Python code. So in this Python code, it needs to call the Groby library and embed both the initial conditions and these constraints into Python variables. And hopefully this code is bug-free and it can transfer these initial conditions and the constraints to the Groby solver and solve this problem. So this is a detailed look of this pipeline. So since this is a completely new problem, we prepare the whole training data from scratch. We pair samples with informal descriptions and formal constraints and Python code. So later you will see that we can use the supervised fine-tuning to fine-tune our model. And we do have our design space or search space where we can exhaustively iterate over the design space, where by which we prepare all these 2 million samples. So we consider two equations, and with different number of constraints, we can scale to more constraints, but that will lead to much more number of samples. So we have 2 million samples, which we believe that will be good enough for our fine tuning. And as I mentioned, that we have the paired samples in this stage, so we use supervised fine tuning to train our model for both the auto formalization and the code generation part. And so we also have multiple metrics to quantify the quality of our auto formalization and code generation. I'm not sure if I have enough time for this, but I can come back later if I do have time. So basically, the takeaway is that because the quality of the auto formalization and code generation are largely separated, that's why we need different folds of the metrics to individually quantify the quality of each component. I can come back later if we do have time. All right, so here are a quick overview of the performance. So if we evaluate on our synthesized data, then if we compare with some open source model or some closed source model, essentially on different metrics, either the auto formalization or the quality of the code, we can outperform, largely outperform other models on both equations. We also spent some time to set up some Zoom surveys to try to recruit some students with different backgrounds and different degree levels to help us write some real-world samples, because we find that when human write some samples, there will be much more noises, say the order of the constraints or the word usage, and they may even have some missing parts. So in general, these real-world problems will be much more noisier than the synthetic data we prepared. So we find that largely on these real-world human-written problems, these models will degrade. But still, if you combine all these three aspects, our model can still outperform other models. Okay, I intentionally quickly go through the first part because I find that the reasoning part will be much more interesting than the auto formalization and the program synthesis. So as I mentioned, that if we only have this naive pipeline, then the solver will directly solve from the initial condition to the end of control. Now we want to introduce another reasoning step into this pipeline. So here we will introduce another language model called the controller, which will try to do some multi-step reasoning and propose some sub-goals into this process. So if we do have this reasoning step, now the solver will not directly go to the end of control, but it will first try to solve an intermediate problem and reach at the new system state, and then resume the solving from the new system state to solve the original problem and reach at the end of control. So you will see that once we intelligently insert this reasoning step, then we can achieve better control utility. So you will see my justification and all the methods and results. But here I just want to leave you an impression that what we inserted and what the pipeline becomes. So now we have two steps here. And in this step, you will see that when we train our model, we actually scale up our data by distilling the knowledge or preferences from these scientific tools. Yeah, sure. Okay. Okay, sure. So before I dive into any technical part, I want to first try to convince you with some justifications why we believe it is possible to do this reasoning step on PD control problem. So the rationale is that PD control is largely a non-convex problem. The reason is that the way we quantify or calculate the control utility is by using a lot of rules. So suppose we want the solution of the PD dynamics to be greater than these linear constraints, then we need to subtract these linear constraints from the solution. If we reverse the inequality, then we need to reverse the sign. If we have multiple constraints, then we for different cases, we either need to use min or max to combine different rewards. So it is because of these different operators that makes the objective of this problem to be non-convex. So we know that for non-convex problem, we may have some weird loss landscapes. The solver may get stuck into some local minimum or some saddle points. So that's the key rationale why we believe the reason step could be possible for this PD control problem. So essentially, we want to find some ways to avoid the solver to get stuck into some barriers from the initial condition to the final state. So we want to actually find some better initial condition that can avoid the solver from jumping to or get stuck into some local minimums. And if you have any experience in, say, in training deep networks, you know that if we train from scratch on the Cypher 10, then we may get some bad results. But if we have the ImageNet pre-trained models, this good initialization will lead us to better performance. So essentially, we are doing the same thing. We want to find some ways to help the solver to start from a better initialization than the original naive initialization. And the key here is that how do we intelligently find this better initial system state or initial condition before we actually solve this problem. Right. So hopefully that justification can convince you that we do have some room to improve by introducing this reason step for this non-convex problem. So the key technical part is that now we want to leverage language model again to help us more intelligently find in this intermediate step. So now we introduce another controller language model whose role is to introduce and find this sub-goal problem. So originally, without this reason step, we start from the initial condition, and suppose we denote the problem, the constraints as phi, then the solver will solve this phi and reach at the final system state, and we denote the reward as the reward of phi. Now we have a intermediate state where the subgoal is proposed by this controller language model. We denote this new problem as phi prime. So essentially, it could be an arbitrary difference problem deviated from the original problem. So we first solve this phi prime and reach at a new system state denoted as u prime. And we roll back to solve the original problem, the phi here. And now we reach at the new final state. And we can, of course, calculate the new control utility, which we denote as reward of phi given phi prime. So that means you can imagine that different phi prime will lead to different utilities. Some good phi prime will improve this utility. Some bad phi prime will actually degrade this utility. So now this problem boils down to how to find better phi prime that can improve this conditional control utility. So the way now we definitely need to fine tune our model. So the way we prepare our data is to run the perturbation to the original problem a lot of times. And you could imagine that different random perturbation will lead, some of them will lead to improved control utility. Some some worse perturbation will lead to degraded utility. So we collect lots of simulation results and pair all these perturbations into winner and loser pairs. So in each pair, we have the winner solution and loser solution. So winner solution, if you plug into this pipeline, it will lead to better control utility. The loser solution, if you plug into this, you will get a degraded reward. So we collect lots of these preference pairs. Traditionally, people call it the reinforcement learning from human feedback. I just borrowed this word, but actually this preference is coming from the solver. So all these feedbacks are coming from the solvers. So you'll see that actually I'm actively distilling the preference from the scientific tool into our training data. And then we use the so-called the DPO, the direct preference optimization, to fine-tune the distribution of this language model towards the distribution defined by this winner solution, and then gradually deviated from these bad solutions. So that means after this fine-tuning, the language model will roughly know how to map this unseen problem to the distribution defined by this winner solution, which can lead to improved conditional utility. And we prepared over 10,000 pairs for this reinforcement learning fine-tuning. And due to time limits, I think I have to skip these different metrics. And we have different difficulty levels. And here are some numerical results. I think I have to skip this number of results. I can show one demo. So in this demo, the first row where we have no reasoning step, so the language model will just naively do the auto-formalization and code generation, and then the solver will be executed and get this solution. And the second row, where we'll actually insert a reason step, which is indicated by this red vertical line. So that means before this 0.1 seconds, the red vertical line, the solver is solving a new intermediate problem proposed by the controller language model. And after this 0.1 seconds, we will switch to solve the original problem. So you'll see that because actually it's a little bit hard to see, but before the 0.1 seconds, the color bars in the second row will be different from the first row. And because the first 0.1 seconds, the system are solving different problems, the system behavior will be different from the first row. And this different system state will lead to further different behaviors afterwards. So if you run these two simulation, and then you calculate the control utility, our control utility will be better than the system that without this reason step. So I think that's the most interesting part, that we can find ways to ask the language model to reason about this problem and find some better improvements that human may have to do a lot of try and trials and then find the room to improve. I think I can stop here for a little bit and before I dive into the next part. Yeah, sure. Mm, mm. Yeah. Mm. Yeah. Mm. Yeah. Yeah. Mm. The group resolver will do that because basically we discretize the spatial temporal domain, and essentially these you essentially solve the linear system, and the essentially is ax equals b linear system, and the A matrix will be largely diagonal because you use say the finite difference to estimate the gradients. Or yeah, this part is simulation. Yeah. Yeah, that's the solver's job. Yeah. Mm. Yeah. Yeah. Exactly. Exactly. Mm. 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 Yeah. Mm. Neural operator. Yeah. They still need to do the discretization. So essentially, they have that's called the resolution of the solution space. But the mechanism is different. So neural operator doesn't do any forward propagation. So it's essentially a forecasting problem. But in solvers, essentially you need gradient in the past to estimate the next step. So yeah, they have different mechanisms. Yeah. Uh, I think that's the first. Yeah. Mm. Yeah, we have different models. Yeah, all of them are fine-tuned. All these, we have three models. Let me go back to the. So we have three models: the translator, do the auto-formalization, the coder. Yeah, all these three models have been fine-tuned. Yeah. Yeah. That's a good question. Actually, I couldn't remember. So we do have the random seeds and the variation, but yeah. To be honest, I don't remember which part has the most variance. Yeah. I mm. So first, I really don't remember, but I suppose the controller will introduce more variance because these two models are fine-tuned with supervised fine-tuning, which means they have paired data. They have the ground truth. But the controller is trained with reinforcement learning and is trained with much fewer samples. And this task will be more challenging than this supervised fine-tuning. So I would say this one will introduce more variations here. Yeah. Mhm. Mhm. So first, we didn't try to say for the same initial condition, we didn't try to progressively add more and more constraints. And for the first part, uh, essentially how this problem is optimized, I think it's a little bit hard to give a precise step because I'm not an expert in the solving in the solution of the mixture of integer of linear programming problem. So all I know that the solver use the algorithm from the branching heuristics to find variables to branch branch and count. Yes. But mm, yeah, I think so. Yes. Yeah, I think so. Yeah. Yeah, I think that should be the process. Yeah, yeah. Thank you. I think you have a question. Oh, so actually, this quite different from neural weighter. So, if you, for example, if you really want to use neural weighter in this setting, then you essentially you are replacing this groupie to your neural weighter. Yeah, yeah, yeah.
The final thought.
Mhm. Uh, One hard thing to animate here is that so we animate the temporal steps using using the animations. So that means this colorful bars doesn't mean that they need to be satisfied across all the temporal steps. So perhaps some of the constraints are only need to be satisfied in certain temporal domain. So even you see that perhaps at the end of the simulation, the black curve violates some of the constraints, but they just need to be satisfied in the certain temporal steps. Yeah. But it's hard to show the animation. Yeah. Yeah, exactly. Yeah, essentially it's 3D, yeah, but it's hard to animate. Okay, I think I want to quickly go through the second project. All right, so the second project will be about formalizing the PD analysis using Lean. I think I can quickly go through it. So I can largely skip this because I think most of the audience are familiar with this part. So basically, we want to formalize the math and do the verification and decompose the problem into pieces so mathematicians can collaborate together to solve the problem. So we try to take steps to formalize the PD concepts, which are largely missing in the current MathLib. So as you already know that people do this formalization and proofs in VS Code and or write all this Lean code. But one problem before we actually can really take step into the formalization of the PD step, PD topics is that we find the MathLib itself is already large enough for people to find a hard time to find what they need. So right now, MathLib has over 200,000 theorems and over 100,000 definitions. And in contrast, Python and C++ only have around 100 built-in functions. So that means and also, if you read the documentation, you will find that the MathLib has lots of missing descriptions and many naming convention issues and perhaps some hidden compatibility issues. So that means for mathematicians to correctly locate the definitions or theorems they need, actually essentially to find the needle from the ocean of the MathLib, which is largely not sustainable for all these mathematicians who work on formal math. So we want to know if we can build an intelligent search engine for people to more efficiently find the definition and the theorem that they need. So before all the techniques, naively, we want to use some language models and build some training data and do the contrast learning. Essentially, it's a code search problem. And then we can build a search engine to help people to translate or embed any queries human researchers may raise and then match the best aligned formal definitional theorems to your query. So essentially provide some candidates. But there are some problems. So if you basically due to time limits, I think I can skip this. But essentially, there are some domain gaps between naive informalization versus some real-world queries asked by a human on Zulip. And another question is that human may ask questions from different perspectives, like some vanilla llama search, or some proof engineering issues, or some meta programming issues. So basically, humans' queries are largely biased. But if you prompt the language model to informalize these formal statements, essentially it will take a very neutral perspective to give you the informalization. So that's the reason that caused this domain gap. And so we want to know if we can build a search engine that can understand mathematicians' intents, that can better serve the retrieval problem. And actually, another issue is the data scarcity issue, because even we can try to collect enough human queries from Zulip, actually, there are much fewer queries from Zulip that has high quality for us to train our model. And also, these real user queries are really paired with ground truth. So usually, they are just a bunch of discussions, and no one really knows what's the ground truth to answer that query. So we really need to find ways to synthesize a lot of data that we can have ground truth, and also to stimulate these real human queries as much as possible. So we build this pipeline. I think I can skip the details, but the core idea is that when we synthesize our training data, we specifically bias and prompt the language model from specific perspectives or intents that we summarize from real user intents. So what we did is that when we feed into the language model, the input have two parts. One is the specific user intents, basically from which perspective we want to ask this question, and the link statement. That's how we prepare the data set and also during the inference. And then we prepare the large-scale synthetic user queries, which is much larger than the naive informalization. And then we fine-tune our model. And essentially, in this process, all these training data are the statements are already verified by the link solver. So here are some results. I can skip them, but one interesting finding is that essentially we need to compare with ChatGPT, right? Because that's a very straightforward solution people want to use. So we find that for both performance on these synthetic data and some real-world data where we conduct some user studies, we largely outperform the GPT models. So we hypothesize the reason why we can outperform the GPT models. We have two reasons. So first is that definitely GPT checkpoints has delayed memory because messages are keep being updated, but the GPT model their checkpoints may be trained several months ago before that. And another concrete reason is that even we enable the web search mode for the GPT model, since the GPT model want to return you the results in a short amount of time, it's very hard for them to comprehensively search over this large-scale database. So that's why our dedicated model can outperform the GPT model that try to return you the immature results in a very short period of time. And this is also to connect with some language model-based prover, so which essentially we find a little bit gain if we enable the retrieval-based retrieval augmented generation for these language model provers. And we didn't just stop there. So at the beginning of this project, our ultimate goal is not to publish some paper, but we want to build some tools that can actually be useful for mathematicians. So that's why we built this tool called the Link Finder. It's active online, so you feel free to use them. So we basically it's a web tool that people can largely input any queries, either in formal language, formal statements, or even proof state. And you can try to retrieve the most aligned candidate formal statements for you and list it here. And we do have lots of active users. So the last time I checked, we have around 200 or 300 requests per day. So I think this is really making some impact in the AI for math or formal math community. And we do receive lots of positive feedback from the users. And this is still not the end. So this is definitely good that we do contribute some real impacts into the community. And this actually a mutual benefits. So after we launch this service for a while, we do collect some preferences from users. So you can see there are some upvotes and downvotes from this web service where people can click which retrieval they prefer than other retrievals. So we collect these preferences, and this real world preferences become the fine-tuning data for us to further refine our model using reinforcement learning. So in this whole process, we complete our story. That's beyond this prepared synthetic data. We further use reinforcement learning to fine-tune our model by leveraging the human preference we collect after we launch the service for a while. So I believe that this is a very good case that's targeting a real world service can be a mutual benefit to both the community and we researchers. And then based on this formalization tool, we start our journey to try to formalize the missing PD topics. Actually, it's an ongoing project because we actually find that even with these language model tools, it's still a it will take a very long human efforts before we can complete them. So we are targeting two levels. One is undergraduate PD book, other one is a famous events book. For both two books, right now we only focus on a small piece of sub chapters to first try to complete. So for the undergraduate PD book, we first focus on the heat education because the fundamental solution is a little bit more simple than the wave and the Laplace equation. For the events book, we try to first focus on the Galerkin approximation method because we find that it will be useful if we want to move step further to solve some well-posedness problems. Okay, so I think that's the conclude of my first part. I think I can largely stop here before we want to talk about other topics. Yeah. Thank you. Yeah. Yeah, I think we do have these results, but I don't think we show the results here. But I think I can at least show this part. So essentially, number of constraints may not be the best way we define the difficulty level because sometimes if you have 3 constraints, that doesn't mean that your problem is essentially harder. So essentially, we quantify the difficulty level of different problems by seeing if you randomly perturb the constraints, how likely you will get a better solution. So essentially, there are some problems that if you randomly perturb the solution constraints, then you can largely get a better solution. But for some problems, it's always very hard to find a better solution. And we do report the performance on these 3 difficult levels. But so we didn't report results by number of constraints, but by these difficulty levels. Yeah. Thank you. Thank you very much. Thank you. Thank you.